I'm Devin with Downforce Racing and IAG Performance, and I'm here with Paul from Verus Engineering. How you doing today, Paul?
Good, how are you?
Not too bad. So the reason we'll be talking to you guys is you guys voted that you wanted to hear more technical stuff from us instead of our plan of talking about products and behind the scenes and kind of keeping it simple. We'll go into a little bit more technical, but keep it so that everybody can follow along at all technical levels. So first thing we'll touch on is the racing loads. You know, different things that you see when you're racing. You see like loads from acceleration, braking, and cornering, and all that translates to lateral forces and cornering potentials. That all ties into what we'll touch on the most today, which is lift and drag. You know, so we can understand that lift is basically like when your car wants to like take off like a plane, like you see on drag strips and stuff like that. And, you know, here what these guys here at Verus do, they do negative lift. They help prevent the lift that we do not want. You know, we want to have downforce that like counters that. It increases the vertical load on the tires, which makes more cornering potential, you know. So one of the things that I have on my car from them is the wing. Was kind of a prototype. They did test it in a wind tunnel and do all this to test how it was going to be having negative lift.
Yeah. So a lot of what you're seeing on actual like car, at the end of the day, it's what hits the tires that matter, because the tires are the only thing that's connecting the car to the road. And the good thing about downforce is that it allows you to use more of what's available actually in your tires, and that's how you get more grip. So as you add more downforce to the car, you get more actual lateral force available per slip angle for the tire, up to a certain point. But for all extensive purposes, more downforce is going to get you more grip on the tires.
So when you guys are designing these wings, you know, you take into things like the Cadona effect, and you take into things like, you know, the airfoil, the thin airfoil theory, especially you take that into consideration when designing these. You know, I think Bernoulli's principle is probably the best way to describe how these wings work. You know, basically in like layman's terms, like, you know, when fluid velocity, and to say fluid velocity, like airflow is basically fluids as the same thing. Like fluid dynamics is very aerodynamic. There's still friction, you know. So, you know, fluid velocity increases, then pressure decreases. And I think the basic way that I like to describe it to people basically is like, if you think of an airplane, you know, and how that wing is curved, you know, like it's curved on the top, and that causes the air to speed up and reduce pressure. Well, what you guys do is you flipped it, you know, according to like the couple theories that we'll talk about. And, you know, it's upside down in a way. So like the curved side is down and the high pressure sits above the wing. And that's kind of how we start to make downforce. But there's a lot more that kind of goes into that, you know, a lot more calculations that you guys do to make sure you have the right curve, you know?
Yeah. And so there's like, airfoils are an interesting subject because there's a lot of different designs. There's a lot of different things you can do to actually make it good, and there's reasons why some are good and some aren't as good. There's a lot of airfoils you can also go online and grab that have had a lot of study on them. Most ones for like a race car are going to be considered like low speed aerodynamics, which is usually anything under like 350 mile an hour, which is going to touch almost anything in the racing world unless you're doing like land speed stuff. So like there's like a specific set online that you can actually download. You can look at these, you can see what they do, and it's all like 2D. So you'll see lift and like coefficient of lift, coefficient of drag, and they're very optimized because it's 2D. So you're not actually getting the full effect of what it would be in full 3D. But that's a good place to start, and that when we first started developing wings, that is where we started. We started with an off-the-shelf wing, and from there we started optimizing it, figuring out what was working, what wasn't working, how we could make more downforce while still keeping the same amount of drag, because our goal is always to make as much downforce but also keep it efficient. And that's kind of where getting into a lot of the theory stuff and actually fully understanding how wings work is where you can really start to kind of tweak at some of that stuff.
So, yeah, I think, when we talk about lift, we can relate it to, like people that have splitters on their car, or not splitters, should I say? They have like the spoilers on their car. And I've always understood them as a fun way of being like, spoilers, they spoil the airflow basically, because if we have too much like lower pressure, on the rear of the car, that's when like we have like the airplane lift start to happen that we don't want. So the spoilers like
Yeah.
cancel that and cancel out the lift that we don't want, and and I know you can add more to this, but when most people look at these CFD graphs and stuff, they see like, okay, we want the higher pressures are wanted on the upper part of the car and lower pressures are wanted on the underside of the car. We want to create like this proper vertical load on the cars. But I think there's a point to where you and I have briefly spoken on that we would have the underbody also add with that. So we do want some pressure underneath the car, not keeping most of it over the car.
Yeah, and with the top side of the car, the interesting aspect is, yeah, you do want high pressure on the top side of the car, but it's also one of the hardest places to make high pressure because just the way a car body is shaped, it's I wouldn't say it's like the bottom side of a race car wing, but it's more similar. So if you look at like any of our CFD images, like usually like a lot of the peak low pressure is actually above the driver's head. As it goes past the windshield and around and it starts going down, you have a lot of low pressure, which is wanting to pull the car up. So that's creating lift. And like a spoiler, what it does is it'll spoils the air in the rear and it increases the pressure a little bit upstream. So it gets rid of some of that lift creating. A lot of times, if it's well designed to, it can also decrease drag, which is another benefit of those. And that's where it's a little bit different than a wing because a wing is actually should be in more free stream air and actually has low pressure on the underside, actually creating real downforce. And then you do have some high pressure on the top side. But in the scheme of things, the high pressure is doing very little work compared to the low pressure side of the wing. And on the underbody is like a really kind of unique kind of thing. And I think a lot of people will really notice that if you look at like Formula One cars. You see a lot of these like winglets, and you see, especially on the barge boards, which if you don't know what that is, that's like the angled looking wing behind the front tire that goes in like by the side pods. And you see all those winglets, and what are these things doing? Well, what a lot of it's doing, some of it is controlling air around the side pod. Other parts is it's actually directing vortices underneath the car. So it's injecting high energy airflow underneath the car, which is going to then create more downforce. So when you're talking about splitters and then you start putting diffusers on splitters, or say you do like a wing on the front instead of a splitter, which isn't as common on a like a street car looking thing, but it does happen sometimes in Time Attack. It's kind of working a little bit different than what you would have with a rear wing. So if you put a front wing on the car, you can't be as aggressive. That's one thing that's why, again, looking at open wheel cars, they have all the winglets on the front. So it has to keep the air energized because there's already so much energy going underneath the car because of the amount of air going there and the amount of space there is. And it's all about getting mass flow underneath the car. And diffusers help that. So you put diffusers on a splitter. Basically what that's allowing is you're not really looking at the low pressure on the actual diffuser itself. You're looking at what that's doing in front of the diffuser. And since it does create a low pressure point on the throat, which is a throat on a diffuser is just the entry, like it's where it just starts increasing in height in essence. And that's what that's going to do is it's allowing more mass flow to actually come underneath the splitter. And with more mass flow, you're going to get more velocity. And then we go back to, or higher velocity. And then we go back to Bernoulli's equation. Higher velocity, lower the pressure. And with downforce force is just pressure times area. So if you have a splitter and you have a fixed area, the only way to make more downforce is to decrease the pressure. So if you can add diffusers, you're going to decrease the pressure on the bottom side of the splitter, and you're going to make more downforce.
Right. So I also think that adding a splitter along with the diffuser keeps too much understeer happening as well with the cars. Because if you add too much rear downforce, like if we just throw like a huge wing on the car and we don't properly balance it, it's not going to be a good day for you.
Yeah, and that's an interesting thing that we're still working out between because like we have a local track and like a lot of our shop cars that we develop, we have a professional driver. He used to race an IndyCar and like kart back when IndyCar was split between kart and that, and he drives our car, and we found that he likes a different setup than say the average enthusiast likes because we've had like other guys out there also drive the car, and a lot of them actually like a lot more rear downforce than the professional driver does because it's a little bit more, it's safer. Having more rear downforce is definitely safer than having too much front downforce, because understeer is more controllable than oversteer. So like it's a interesting balance, and we're constantly working on figuring out a good way between like a good balance for like a novice driver and somebody who's a little bit more advanced. And we try to we and if we're doing a bigger type of build like with like a time attack car, and we might want to build in some adjustment, which is most rear wings have a good amount of adjustment. One of the things we develop like on the wing that's on your car is there's a lot of adjustment that you can actually do to help tune in that, yeah, to tune the aero balance.
Yeah.
Because everybody has a different driving style. Even professional drivers, like you talk to race engineers on race teams, every driver is a little bit different, and they're going to want the car set up differently. So you need to have that adjustment in there. It's no different than suspension. Everybody's going to run a little bit different as suspension setup. You might like a little bit higher spring rate. Somebody else might like a little lower spring rate or different anti-roll bars. Like all of those things are part of it's car setup, but part of it's tailoring a car to the driver, and it's no different with Aero.
Right. And I think that changes as a driver progresses. Like I know when I'm still learning, but like when I was first learning this car, like my setup has changed gradually as I get more comfortable, as I want to take more risks and become more aggressive. So breaking out of that comfort zone and of course eliminating some of my bad habits of driving, like my setup has changed a little bit. And I think most people will find that you're not going to just buy a cookie cutter product. Like, when you buy a product from you guys, it might evolve and you might need to talk back and forth a little bit and figure out where you're at now and what kind of are your end goals. I know that's what I did with you guys. Like, here's where I'm at, here's my end goals. And we came up with this, that I can adjust it as we go.
Yeah. And having that adjustability to keep improving, because once you keep improving as a driver, you learn the car more, you can push the car harder, you can start doing things that you wouldn't have felt comfortable with before, and you're going to start going faster even with a very similar setup. Like you could still maybe add a little bit more rear wing and yeah, to increase a little bit of drag, but you might feel more comfortable to take corners faster. And just because you lose a little bit of speed in the straightaway, honestly, a lot of times that doesn't matter that much. A lot of people focus on that more than how much time you're gaining in the corners. You're spending way more time turning on a track than going straight. So if you can take away even a small amount of time on those corners, it's awesome. That's why Aero is very beneficial to even a novice driver, because it just makes you feel that much more comfortable to take corners faster.
Yeah, I feel like it makes the car way more planted. Like when we talk about, in the beginning of the video, when I touched on the different loads that you see in racing, like when you're accelerating, when you're braking, cornering, all of that, like different vertical and lateral forces that we're working with, is the Aero is going to help balance that out, because I don't think really production cars are capable of that. That's why you have body roll and horrible accidents when certain cars go over 110 miles an hour. They can't handle that, they're not balanced correctly.
Most of the cars like that we test stock, except a small few of them, create lift. It's very, very common for any street car to create lift. And the balance is usually weird because, and it took us a while to kind of get our head around it, but a lot of times we're kind of to the point where we don't think OEMs focus a lot on the balance side of things, because one, it's not a whole lot of pressure, and two, you're actually creating lift, so it's not as much of an issue. So the balance is always super weird on a factory car. So like every time we'll like run CFD on a factory car, it's always like, oh, I wonder what's gonna, like, how is this car gonna act? Like the new one that we're just starting, that I'm working on the CFD model for, is actually a Ford GT350, like the S550 ones. I have no idea what it's gonna do. No idea. So it's like, that's kind of the cool part of like what we're doing, is it gives us like, every car is a little bit different, and you never really know what to expect until you start doing some testing.
Right. And I think that's what's great about you guys, because like even when it comes to, you know, some of the splitters and rear diffusers I've had prior, like, you know, when you think about a splitter, like it's basically trying to make all that pressure build up in the front of the car and shoot it over, or, you know, sometimes under the car as well. But it's like, if you don't have a good product that's just going to kind of be flimsy, it's really not helping your cause. You kind of still have a stock car in that sense, you know, like what you guys do, you test that. It's not just for looks. Like I don't just have a cool rode out car, you know, it actually is performance related.
Yeah, splitters are, we really like splitters here for production stuff, but we also hate them at the same time, because they're the most they're like, if you look at them, you're like, wow, this is really simple. But in reality, it's the most difficult part for us to handle, because a lot of times on the front end of a car, there's no good place to get good mounting locations. Like the bumpers are always weirdly shaped. A lot of times they're angled, and you want to get the splitter fairly flat with the ground. We could go into like rake and stuff like that, and what you want. But in general, usually you target around 0 degrees. And to get things like that to actually work, it's actually a lot of work on our end on the engineering side. Like we're still trying to work on finalizing the Supra front splitter that we've been working on for like 6 months now, and a lot of it's just fine tweaking to get it, not the performance there on the Aero side, but the engineering side of the manufacturing and the installing and making sure it's strong enough and it's doing everything it's supposed to be doing. And that's a huge battle with a lot of splitters, and that's why we really like them, because they make the car go a lot faster. They're very efficient. They're more efficient than, say, a rear wing, but they do have that problem of the more difficult to engineer side of things.
Right. Yeah. I mean, the last thing us racers want is my front splitter coming off when I'm racing. Not a good day. Kind of is a snowball effect. Yep. But, yep. You know, while we speak on like kind of like the area on the front of the car, you know, I think we can transition to talking about like drag a little bit, since those are the main two things I want to touch on today in this video. You know, like if we go back to like the normal like drag equation, we have it that, you know, it's velocity squared with the drag coefficient with the frontal area of the car, touching on kind of the splitter, you know. Mm-hmm. So I like to think of drag about pressure and friction. You know, I basically like to describe it as like, the faster you go with drag, you know, if you don't have an aerodynamic car, you start to like have pressure pile up on the front of it, and the back low pressure is creating a pressure differential, which means your car is going to go slow and your top speeds aren't going to be that great. You know, it's going to affect it. So when we look for Aero, I think we're looking for you guys to have drag reduction. So that way we have faster times, you know, our acceleration is quicker, and, you know, fuel economy does play, especially if you're doing maybe not time attack, but, you know, if you're going to be doing AER or some kind of endurance, like you do want to have some kind of a fuel efficiency to it.
Yeah. And like drags are a pretty cool one, because like the biggest one people think of is pressure. That's what almost, if you talk about drag and you talk about a car, most people think of pressure. And that is a big one. It's not always the biggest. Like a race car, there's actually also induced drag, which is even usually bigger than pressure drag. Friction is usually fairly low on a car. It's actually very looked at on like aerospace though. So that's where like aerospace engineers and like automotive side kind of like disagree, is like their definition of efficient is a lot different than our definition of efficient.
Yeah.
On the friction side, friction's caused. What friction does is it actually creates a boundary layer, which we'll go into in another video, but that's what actually causes that aspect. And then pressure is obviously, if you just stick your hand out a window of a car and that force pushing your hand back, that's pressure drag. And that's what's happening on the entire car. And the bigger the car is, aka the more area, the more force you're going to have pushing it back. You also have your coefficient of drag, which is basically like, it's just a number which describes how slippery it is. Like different shapes. Like if you have your hand straight up, like going vertical, you're gonna have more drag than if you turn it than 90 degrees. So it's like you don't, like given it decreases the area too, but it would also makes it more aerodynamic. It's gonna decrease drag. And then induced drag is a little odd, but it makes sense, and it definitely makes sense when you start looking at wings. It's also why underbody aero is very efficient. But so induced drag is basically you take a surface and you have, say, the bottom side of a wing, and you have low pressure. Well, it's actually acting like a vector, and it's going to be normal to that surface. So on the back side of a wing, like back here, you're going to have an arrow actually pointing rearward and down. So induced drag is basically that X vector. And then the downforce that's creating is the Z vector. And so that's where you start to really, that also goes into wings on how you can make wings more efficient than other wings while still having the same amount of downforce, if where shape comes into effect. And there's a lot of things you can do with that, but induced drag, then on the underside, the why it's so efficient is because usually you don't have those big angles like you do on a rear wing. You're not going to have crazy angles on the underbody. It's a lot more gradual, and you have, so the X vector is a lot smaller, so you're getting a lot less drag. Like underbodies can be as efficient as 300 to 1, and so that would be like an L over D of 300, which basically all that means is you're making 300 pounds of downforce per every 1 pound of drag, where on, say, a really, really good wing would be like 15. So you're making 15 pounds of downforce for every 1 pound of drag. So that's where you can start like fine tuning where things are being done. But a lot of times, a rear wing's the easiest way to make downforce. It's really hard to make tons of downforce on the underbody unless you really know what you're doing and you have a lot of track testing with it. And there's a lot of things that go into that compared to, you can put a wing on a car and make a lot of downforce. Yeah, and then you can put a splitter and balance it out and you can make a lot of downforce. And it's still, in the scheme of things, very efficient for what a factory car is. So comparing a factory car to adding a wing and a splitter, it's not that far off. You might lose a mile an hour on the straightaway, but as long as you're making that downforce efficiently, you're still, the amount of downforce you're adding well overweighs the smidge bit of drag. But if you have an inefficient setup, you could be dropping like 5 miles an hour in the straight and still not gaining any more than an efficient setup in the corners. And that's where efficiency really plays into the role.
Right. And, I think that for me, when I did aerospace engineering for a while. So going to Embry-Riddle, like they were really big on different like drag coefficients, and it's kind of different when you look at automotive versus like airplanes and stuff like that, but I always find it fascinating that when you look at drag coefficient that the F1 cars don't make sense, like compared to like what you think they would be, like I would always understand like, basically like a teardrop is like the perfect, most aerodynamic thing out there, you know what I mean? And it's like, has like a coefficient of what, 0.005 or something crazy. And then you look at like an F1 car and it's a 1.1. Like what?
Yeah. If you're like, 1.1. And like, so, and like the average car, I would say, if you have like a car that's trying to be super efficient, you might be like 0.25. That would be really, really good. And then I would say most cars are probably in the 0.3 to 0.35 range. And then you have some like boxy cars that are in the 0.4. But really that's like on a factory setup, that's about where most of them lie, which is actually a pretty big swing between 0.25 and 0.4. That's pretty big when you're actually doing the math and you look at how much force is actually being applied at like say interstate speed. That makes a difference, or race speed, which is even more.
Right.
On our end of things, a lot of what we're looking at is we're looking around for a lot of setups somewhere around 0.4, and then to get much more than that, you're really starting to do a bigger build, like with our bigger wings. You might get into like a high 0.4, like 0.45, 0.48. maybe even 0.5. Now, a really efficient, like crazy time attack thing, I would say around 0.7 is kind of where like a lot of ours end up. But that's making a ton of downforce. So it seems like, oh man, that's a ton of drag. That could be like maybe 3 times what the factory car does. Well, yeah, but you could be making 10 times what the factory downforce is. And
Exactly. Yeah.
there's a lot of things that can kind of go into that, but the drag coefficient, and that's not the only thing to look at. A lot of thing that was hammered into us at schools when we were doing like the fluid stuff and aerodynamics is make sure you actually look at CDA and not just CD, because you could be running analysis and, oh yeah, my CD keeps going lower and lower, but your cross-sectional area is actually getting larger. And so when you multiply those two, your number is actually still getting bigger, which is worse. So you need to look at both of those. So usually like when we're doing stuff, like I don't even look at CD, like coefficient of drag. I usually look at CDA just because that's the most relevant for me to make sure that we're not, like, I'm not screwing up on my end.
Right.
Because
Yeah.
it's easy just to get like looking at one thing and overlooking another aspect. Because when you add a splitter to a car, you add a rear wing, you are increasing the cross-sectional area most of the time. Not always, but most of the, you could put a wing low and things like that. It might not be very wide, so you could actually get it behind the full car and not increase the area. But most likely it's going to increase the area of the car.
But I mean, I think that a lot of us need to ask, when is it the right time to start adding downforce and things like that to our vehicle, you know? And I mean, you know, chime in with this, but I definitely think, you know, when you have the correct camber and toe settings, you know, I think that is when you need to start looking into downforce. I think like suspension should come first. You like do your mechanical grip first and then start to go for the aero so that you see the most benefit from it, you know? I think, you know,
I usually, go ahead.
you know, I think that, you know, at the end of the day, our goal is to have better tire wear, heat distribution on the tire, and faster lap times. Like that's what we want for time attack anyways. You know what I mean? So I think people that are starting and enthusiasts kind of need to make sure their setup is good before just jumping right into aero.
Yeah. And I definitely agree with that. A lot of times, and I think mechanical grip is usually easier to comprehend. And then once you comprehend mechanical grip, it's easier to go into a more complex subject, which is aerodynamics, and understand that grip. So instead of like trying to compound both of them at the same time or doing one before the other, because if you're adding a lot of downforce, you're most likely going to have to change your spring rates anyways. If you're changing your spring rates, then other things are already kind of changing that you need to have your suspension kind of squared away. And your suspension is going to change a little bit if you add a lot of downforce. Like you're going to go with a higher spring rate on a car with aero than what you can go with a car without aero. But in general, you should have a pretty solid mechanical setup before going into aero. And I think that usually makes things better. And like when you should jump into aero, pretty much like I usually don't think that you can add too much downforce most of the time. Most people, so honestly, adding aero is usually beneficial all the time. A lot of people focus a lot more on drag on cars than I think they fully need to. Like drag's definitely important. Like I don't want to be like, oh, who cares about drag? But like if you start making downforce, your times are going to decrease on the track. It's no doubt about it. Like we've done enough testing back to back. Like you make downforce, your times are going to go down. And the one benefit with your times going down is it doesn't actually matter if you're a professional or a novice driver. Your times go down either way. Like you could be a terrible driver and adding downforce, you're probably still going to go faster. And that's kind of the nice thing that a lot of people do like about it. Like if you just want to keep going faster and faster and maybe not improve your driving skills sometimes, you can slap aero on and still go faster. Like I'm not saying that's the best way to go, but that is it usually works that way.
Yeah, I can definitely see that. Yeah, you know, and I do think when people think about adding aero to the car, I think that we agree that our goal with that is to like have the most downforce we can with the littlest gain and drag, just to make like the best efficiency that we can have, you know. I think that at the end of the day, that's our goal with that. But and I like being able to work with you guys with this because you actually test that. So I can actually go to you with this stock car and you know what's going to work on it. You know, you test it. You have the CFD. You know, you actually do real world testing to be able to figure out what's going to work for the application at hand. You know, it's not a cookie cutter kind of thing.
And we can get another benefit is since we've done a lot of the testing, we can give you recommendations on, like, say the car's doing something that you're not expecting, and it could be aero related, and we can be like, oh yeah, maybe try changing this. And because we've done enough testing, we can actually problem solve, where if you're just slapping random parts on your car, it's very hard to call up somebody and problem solve when they probably have no idea what it's even doing in the first place. Like most of the aero stuff is usually looks related. Some of the companies have data and they do a decent job at it. Some of them don't, and I don't usually recommend those. There are other companies that do good work, and they're not bad, so I don't have a problem. Like I just like people who actually put the effort in and come up with actual data, and then you can actually properly educate the customer on like what it's going to do. Like when I put this wing on the car, what is it going to do?
Right.
If I put the splitter on the car, what is it going to do? Okay, I have both these on the car. I'm going to put new springs on. It actually lowers the car 25 millimeters in the front. What is that going to do? Well, we can give you an idea of what kind of aero balance shift you're going to have, how much more front downforce you're going to have, everything along those kind of lines. Like, because we've done that type of testing to know what this does.
Right. And you mean you manufacture these in-house too, so you do control the shape of the wing and all that. Like, you know the kind of shape that it needs to be, to make it the most efficient. So
yep.
Well, I think working with you guys has definitely helped with my program. I think it can help with other people's program. And hopefully, like, talking about lift and drag a little bit with this, we kept it so people can understand. I feel like that's really hard for you and I and probably Mike Kiwajima to do. So I hope like people can like listen to this and make an informed decision, that they can come to you guys with their application and be like, I want race car. How do I make race car? And, I think that the next video that we do, we definitely touch on like my favorite, like the Reynolds number. We start talking about like the laminar flow and, we start talking about boundary layers and get more technical, since I think a lot of people want technical because they don't know. And there's not enough information out there. And I don't think people kind of know what they're talking about enough to like explain it, to be honest. So I hope
it's hard to even know what to search for.
Yeah,
it's hard to even know what to search for online to even figure out exactly what you're trying to even figure out. Like if you didn't go to school for like any sort of engineering, it's very hard to like just get in and really find the information, because a lot of the information's terrible, and then to actually find good information, it's confusing, and you have to like go back and forth between multiple different pages to try to figure out, okay, what is this actually telling me? So like there's a lot of things, like especially with Reynolds number and turbulence and laminar is a big one for me online. It's horrendous. Most people it's
Well, hopefully we clear a lot of that up on our next video. I hope you guys enjoyed this. Hopefully it made sense. Leave us a review. Let us know what you think, because next week we'll be going in a little bit deeper and on your favorite subject, apparently. So please, if you guys have questions and you want setups, I'm not 100% biased on you guys. You guys have persuaded me to be, but I think that you can go to Verus, you can talk to them about your needs, and they can at least point you in the right direction with data to back it up. And I think that's what makes an educational decision rather than, oh, I just like them because they're awesome. So thank you for taking your time with me today, and we'll see you guys next week.